Okay. So we are going to look at data modeling today. In a way, we've almost kind of been data modeling already, because we just haven't been doing anything in context of a situation at all. We have looked at fitting a graph that had the right amplitude, period, midline, all of those things. It just wasn't in context of an actual situation. So we have already seen f of theta equals a sine b parentheses theta plus c closure parentheses plus d, or that similar equation for cosine. So we are going to just be working more and more with that, both with and without the calculator. It's going to be pretty important that we do this without the calculator, because for sure on your AP exam, FRQ number 3 is a non-calculator question with modeling. So we're definitely going to have to do that. You may still run into some calculator modeling questions on the multiple choice, but the FRQ on the exam is going to be calculator inactive there. So here we've just got an example. Let f be a sinusoidal function. The graph y equals f of x is given in the plane xy. What is the period of f? So this is not really a new thing, right? This is just sort of a little bit of review here. I like to draw in the midline every time I have a graph. So midline for this particular graph is at -2. Actually drawing it in helps me see like when I'm back to the place that I started. So if it is possible, I always want to start at the y-axis where x equals 0. Sometimes it's not possible, but it will be possible on this particular graph. So I just trace my graph until I have got back to where I started. Now here, I'm back to where I started, but have I done the full cycle? I'm not. I need the bottom part of the graph here. Right here, I end up back to where I started, right? And then the pattern would start to repeat. So I'm looking at the x-axis here, and that distance right there from 0 to 2 is just 2. So that is our period of the function. Okay, everybody okay here? Okay, if we look at example 2, it says let g be a sinusoidal function where g of x equals cosine of 2x plus c minus 1. The graph of y equals g of x is given in the xy plane. Which of the following values could represent the constant c? So for this problem, again, I always like to draw that midline in first. The midline helps you sort of get a bearing of what are maximum points, what are midlines, what are minimum points. Those are your key features there. Now, they are specifically telling us that we're using a cosine graph right here. Okay. So cosine, does it have its y-intercept at a maximum, midline, minimum? Which one is it? It is a maximum, right? Because we will have this right here just memorized. Y-intercept is at a maximum right here. This graph does not have a y-intercept at a maximum point. Cosine would, though, right? So I like to just draw this in. And you're going to kind of go in like increments of 4 here. So you go from like maximum to midline. So like midline's going to hit here, and then minimum, midline, maximum. Sometimes it may be hard to tell exactly what you're doing there, but if you take your original graph right here, you've got a minimum, midline, maximum, midline, minimum. Your like tick marks that you're looking at should line up with those points there. So if I have this red dotted graph, I already know what the minimum is. They've adjusted for the period for me. I don't have to change that here. I just need to think about the phase shift, right? So I am thinking about taking this dotted graph and moving it to match my solid line. Now my mind immediately takes this dotted graph and moves it to the right pi over 2. That's what I want to do. However, did they move this graph to the right? They did not, because all of your answer choices are positive, right? Which means that you actually moved the opposite direction to the left. So the answer choices have us moving to the left. So if I took this minimum point right here, maximum point right here, to get to the actual maximum point on the graph, I would need to go this distance to the left, which is a distance. We're going from 0 over to pi over 2, so that's a distance of pi over 2 there. And I would choose that one. Questions? Okay, so let's start looking at like an application. Now, some of these things are going to start off kind of silly because we have to let's come up with something to work with here. So we are talking about a yo-yo attached to a 30-inch long string, right? Yeah, I realize that if you are a yo-yo artist, if you are an excellent yo-yoer, you're probably not doing any math on whether or not what you're doing with this yo-yo, right? Think of other things, like anything that's swung around in a circle could apply to the same situation here. So while this situation is a little bit silly, if you were looking at like something different, yeah, could be like that. What are those called? I don't know. We don't do those in like regular track here. But something like that. My mind is going to, this is also a ridiculous example, but my mind is going to, have you all seen any of those YouTube videos where rednecks have the track hoe, like the excavator, and they've hooked up a slip and slide and they're dragging somebody around in a circle over and over again? Also, don't try that. It looks terribly dangerous, but I'm pretty sure that we could get some good velocity and do some analysis of just how dangerous this is if we wanted to. Once again, probably not. I imagine there could be situations in like industrial, complexes where things are spinning where you need to know. Maybe like designing a ride. Like if you're designing a ride for like a fair or like heroines or something, because lots of them spin around and around and around, right? You need to analyze that very carefully before you start building it and putting people on it. So, or you could just do like the rednecks and hook. So, yeah. So you could definitely do this, and like you could add in. We're only going to like think about what the graph looks like, but if you went further, which definitely no redneck is doing this for a good time on a snowy day, but like you could analyze like the forces. Like you could look at what this means for forces. If you were like in calculus, you could look at like your acceleration and all of those things at different points, and you could really like analyze this carefully. Again, with yo-yo, you're not doing that, but it could be stretched to things where it would be much more applicable, right? To like, oh yeah, I could see why somebody would need to do this. So a yo-yo is attached to a 30-inch long string and is rotated at a constant rate. The figure provides representation of the yo-yo in the XY plane, with the direction of rotation indicated. At time t equals 0, the yo-yo begins to rotate. The yo-yo is at the start position in the figure. At time t equals 5 seconds, the yo-yo has completed 20 rotations, and the yo-yo is in the same position as it was at time t equals 0. A sinusoidal function is used to model the x-coordinate of the position of the yo-yo as a function of time in seconds. Which of the following is an appropriate model for this situation? So, we are talking about this yo-yo being swung around. Also, we got to consider that this is not the yo-yo spinning. Like a lot of times, if you like throw it down, like the yo-yo will spin. If you got one of those that spins, this is like you've handed a yo-yo to a 4-year-old. And what is the 4-year-old going to do? They can't yo-yo. They don't know how to do it right. They just start swinging it around in a circle, right? And taking out everything within a 6-foot radius of wherever they're at. So that's sort of the situation that we're looking at. Or I guess you're doing like a round the world kind of trick or something there too. So we got lots of information that we have to consider to decide which one of these is going to be correct. Now, because they made this multiple choice, there's some things we don't have to think about, right? Because whenever I look at this graph, I see that the amplitude is the same for every single one of these, right? So really, they're not making us think about the amplitude in this case. You don't have to come up with that. In fact, what are the only differences in these 4 answer choices? The B value, which affects the period of the graph, right? So we could analyze this much deeper, and we're going to do a few problems where we do. But really, the period's the only thing they're asking. Like, that B value and the period are the only thing that they're asking us for. So we need to think about what the period of this function is. And so the period is the time for one complete rotation. So the information we need is right here. At time t equals 5, the yo-yo has completed 20 rotations. So that is telling me that we did 20 rotations in 5 seconds. I don't really know if right? If I wanted to sort of reduce that, that'd be 4 rotations in 1 second. Now, this is not our period. This would be our frequency. How long does it take for 1 rotation? .25 or 1/4 of a second. I'm going to stick with fractions just because they didn't use decimals over here for this. So 1 rotation takes 1/4 of a second. So, first of all, sometimes with fractions, it becomes a little bit tricky to like know what the B value is. But like for answer choice A, I could think of this as 30 sine of 1/4 times t, right? Because there's like a 1 right here, and I could write the t over to the side instead of in the numerator, and that would still be equivalent. So the B value for answer choice A is 1/4. Is that the right answer? Do we just take this number and plug it in as our B value? We do not, right? So the period, this is our period, is not the number that we plug in, right? So A is not correct because they just took the period and plugged that number in. So probably what I would do for these is I would just check each one of them, or you can find the B value. It can work either way. But to find the period, you do 2 pi over B, right? So B right here is 4, so you do 2 pi over 4. That is going to give you pi over 2. Is that what we want for our period? No, we want 1/4. Not it. Okay. This one also is a little tricky, but this is 30 sine of pi over 2 times t. So that B value is pi over 2. So even though that t is in the numerator, t is your variable, right? So it can be pulled over to the side instead of being put in that numerator. So if I do 2 pi divided by pi over 2, dividing fractions is easy as pie. Flip the second and multiply. And the pi's will cancel, but I'll get 4 here. Is that what I'm supposed to have? No, so I'm hoping for D to work out for me. What is the B value for D? Interesting. It is 8 pi, because that's what's being multiplied by our T. So we'll do 2 pi divided by 8 pi. The pi's will cancel. 2 over 8 reduces to 1/4. This is what we're looking for right here. Okay, questions? Okay. All right, so this next one is going to be a little bit trickier because we have to, actually it's not too bad. It's not too terrible. A little trickier because there's not answer choices. What makes this one not terrible is that they only ask us for A and B. So we're just finding like amplitude and midline for this. So they're kind of like working up to the really hard ones where we got to find everything about the graph. So a clock is mounted on the wall. The point P is located at the tip of the minute hand of the clock. The function h represents the height of point P from the ground at time t, where h of t equals a sine b, parentheses t plus c plus d. In the xy plane, the points 0, 70, and 30, 52 represent a maximum value and a minimum value, respectively, on the graph of h. What are the values of A and D? Okay, so let's think, we can think of this a couple ways. We can think of the clock itself, right? So at 0, right, so here's our center of our clock. At time equals 0, that minute hand's going to be pointing up, right? Because that's where the minute hand points whenever you are looking at an analog clock. And so the height right here is 70. What are we in? Inches? Does it even tell us? It does not tell us, but I'm going to assume we're in inches because any other increment like feet doesn't make that much sense if we're talking about a wall clock in a room, right? So if you think about like the minute hand on this clock, at its highest point it is at 70, right? At 30 minutes, the wall clock is going to be pointing straight down, right, for our minute hand. And then its height is 52 inches. So we really don't have to think about the period of this graph or anything like that. We just have to think about finding amplitude and midline. Okay? My suggestion, always go for midline first because you need midline so you can sort of tell how far away this is, right? How could we find midline if our maximum is 70 and our minimum is 52? Add them together and divide by 2. Just find the average, right? That'll give us the number halfway in between. So for D, our midline, we're just going to do 70 plus 52 divided by 2. So that will give us 122 divided by 2. Did I do that right? Yes. And then that'll be 50 plus 11, 61 inches. Okay, so our midline would be at 61. That's halfway between 52 and 70. How could I find the amplitude for this one? Okay, say that again, Will. From 61 to 70. So if I do 70 minus 61, I will get 9 inches. So I'll get A is 9, D is 61. So I also could have done 61 minus 52. I could have subtracted 70 minus 52. I'd get 18 and take half of it, right? Those are all options here. Okay. Now, writing the whole equation, a little tougher because you got to think about the period and all that. We're going to work up to that, but we're not going to do it on this problem. Okay here? All right. Okay, this one looks like it should be a calculator active problem, but I don't think it is for this one. We've got decimals, but I don't think this would be a calculator active problem. So we've got the average monthly temperature in degrees Fahrenheit for a town in central Indiana can be modeled by the sinusoidal function, and it gives us our function, from 1 to 12. Based on the model, which of the following is true? Okay. So this is going to give us a graph that goes up and down. This should make pretty good sense because, you know, in the summer your temperatures get hot, in the winter they get cold, in the summer they get hot again, and that should just more or less fit that pattern, right? So they talk about the average monthly temperature, but we got to keep in mind that that is a measure that we're looking at, and we need to be careful with reading that as the average of the average monthly temperatures, right? The average of the average monthly temperatures, that's your midline, right? But average monthly temperature is just because they're not giving us, like if we want one temperature for the entire month of April, then we have to add them all together and divide by however many we've got and use that number, right? So this tells us about the maximum average monthly temperature, so the maximum that we're getting for a month, or the minimum. Okay, this number right here, our midline, this would be the average monthly temperature, right? It goes right through the middle of these average monthly temperatures. So, can 61.2 be the maximum of this graph? No, cannot. Because 61.2 is the midline. That's the average monthly average monthly temperature, not this one. Okay, we got the maximum occurs at m equals 1. Let's hold off on that one for a second. We got C, the minimum average monthly temperature is 35.5. How would I find the minimum for this if I can't graph it? I could graph it and I could just click on the minimum if it were calculator active, but I don't think this one will be. Amplitude, very good. So if I take 61.2 and I subtract the amplitude, that should give me the minimum value, right? So that's going to give me 5. Borrow again. And look at there, 35.5, right? So the minimum value here should be 35.5. C needs to be our answer for this one. The other two are going to be much more difficult to consider. because you have to think about the shifts of the graph in this particular case. And I really don't like it very much because they start at 1 instead of 0. But since we have found our answer for this, we do not necessarily have to consider those other parts. For that, we're going to look at that on a coming question where we have to. Okay, here. Okay. What would we do if we wanted to find a maximum? We would add instead of subtract, right? So we take that midline and add for that. Okay, let's look at this. Now, this particular case, we are, I don't know, it still doesn't have a calculator next to it, but I think, let's think about it without a calculator. They might give you this without, I don't think they'll give you this without a calculator. Alright, so N gives the number of nighttime hours on the first day of a given month, where 1 is less than or equal to T, less than or equal to 12. The table gives values of N at selected values of T. A sinusoidal regression with 16 iterations is used to model these data. What is the maximum number of nighttime hours predicted by the sinusoidal function? Here. So, if we're just looking at our data, I don't see a maximum anywhere, right? I see the highest number I see is 11.4, and then I've got 11.3 right here. So, I'm leaning towards, C or D as the answer choice possible there. But 11 and 12 are, neither one of them are exact, right? For this, yeah. Probably. But I would like to look at the regression because it's talking about, so our data doesn't always fit perfectly, right? So since it's asking us about the regression, there is a chance that maybe our regression doesn't quite hit those maximum points because they're going to be like in between a little bit. So I think we should probably look at the regression to see for sure whether we're coming in a little below our points or maybe above the points that we're seeing here. So if we want to do a regression for these, this is the part you will need your calculator for. We are going to go to Desmos. And we are just going to put our data in. And so when we're looking at regression data, you can see, like, I see the pattern, but it may or may not fit perfectly for this. Oh gosh, I also do not like that it doesn't really matter so much. If I do a regression here, sinusoidal regression is an option. Do notice something here. Look at the y equals right here. What do we usually see different inside of this set of parentheses? Usually we have an extra set of parentheses around t plus c, right? So you just have to be careful. It's not going to matter for what they're asking us here. But be careful, C is not your phase shift here. You would sort of have to like factor out the B, or you could type in what we usually use there. So when I put this in, I can see here that this is, I don't like this question, really. Because what are we getting for our answer? Yeah, it's between 11 and 12. It's 11.33 is our maximum we're getting for our regression. And they didn't put decimals on this. This is really like talking, like this part here is really talking about your like domain though for that. So let me look at Mr. Passwater's answer key on this and see. I'm leaving 11 just to round down, but I don't love this question. And he says A plus D, but I mean, I think he just rounds down, but I don't love this question. I would either give more decimals as the answer or give more specific directions in whether or not to round down or up here for that. So he says 11 for that. So, like, I don't love the question, but, like, Evan, your logic is, like, fairly decent that you would want to say 12 because clearly we go past 11. But because they're asking about the regression model here, you can see, like, our maximum of this regression model is 11.33, which is actually lower than the 11.4 that we have. So your regression can come in below your actual values in your table sometimes. I don't love this question because of how much rounding is done here, which makes it, you know, a little bit worse. But it could come in below when they're asking about the regression model for that. A lot of times, it may be. Depending on what you're doing with it, rounding this much is just bad idea anyway. You're definitely not sending a rocket ship to the moon whenever you've rounded and just kind of cut 0.33285 off. That would be disastrous, I'm sure. So that's what we're looking at here.